Hey everyone, in this video we're going to start to look at the reactions of alkenes in more depth. We're going to look at the general process through which they follow, and we're going to then branch out and actually step back a little bit and talk more about general reaction energies, and we'll be able to apply those later as we move forward through a variety of types of reactions. So before we get into those energies, I just want to give you kind of an overview of reactions, or how I can think about reactions. So as we go through this semester and next semester, if you take 2310, our reactions are generally organized based upon their functional group. All right, and I'm going to break those functional groups up into separate categories so you can see how this is all going to fit together. All right, the first type of reaction that we're going to look at is with alkenes, so that's shown here, but we can expand that out and say that this first group of reactions is going to involve reactions of carbon-carbon pi bonds. Okay, so this is the first set of reactions that we're going to look at, and this is going to go over maybe 4 different chapters. The next type of reaction that we'll look at are reactions where carbon is attached to some more electronegative group. So in each of these cases, the carbon is going to have a delta plus, this more electronegative group is going to have a delta minus. All right, these X groups in a generic sense can either be things like halogens, or they can be oxygen, so in alcohols, and these are both what are called ethers. So these are oxygens that are connected to oxygen, two carbons. So this is a special case of ethers. This is called an epoxide. And so it's an ether that's in a 3-membered ring, and we'll go more into the reactions of epoxides than we will of other ethers. Most ethers are pretty stable, but epoxides I always think of are more like a mousetrap. So you pull that spring back and open up the mousetrap, and that's what the epoxide is like. And so anything that comes in that bumps that or budges it snaps that trap open, and it'll snap that ring right open as well. So functional groups that have carbon connected to a more electronegative group, this is going to be the second type of reaction that we're going to look at, and in fact this portion right here is essentially what we look at in chemistry 2310. Alright, so in 2320 there's 2 main categories of functional groups. One are the groups that have carbon-oxygen pi bonds, and so these are referred to as carbonyl groups. Alright, and those carbonyl groups can either be connected to just carbons or carbon and oxygen. This gives us one category, or they can be connected to some more electronegative atom. Alright, so in this case we have about 5 or 6 different carbonyl groups, and it's a challenge in this section because they all have some similarities, but each different group is a little bit different as well. So then the last group that will be talked about in 2320 are what are called the aromatic compounds, and they are based around this kind of prototype structure, which is benzene. And even though benzene has carbon-carbon double bonds, which you would think would put it over into this category, and we talk about that early, when we have this arrangement of a ring with alternating double bonds, it gives this benzene a different type of reactivity, so we talk about it separately. Alright, so this part is chemistry 2320, plus some other things. Alright, so in general, we can oftentimes group them into just a simple concept that involves something with a plus reacting with something that's a minus. All right, and we've seen this before. We could have something as simple as H plus reacting with OH minus, right? And this reaction would go to form water. All right, we could look into this in a little more detail if we look at the electrons and what's happening with the electrons. So hydroxide here has 3 pairs of non-bonding electrons on the oxygen. All right, and so it's one of those pairs that are going to be used to make the bond with the proton on the left. So we could show any of these, and we show an arrow like this, where this arrow shows the movement of electron pairs. We like to use these arrows a lot in organic chemistry. So that pair is the pair that's going to be used to form this bond right over here. Okay? So notice we have plus reacting with minus. So we can label these in various ways. We can call this, right, is an acid. This is a base, right? That's how we normally would do this. And that's if we're just thinking about a proton donor or a proton acceptor. We could also think about it in terms of electrons, right? And so then we could call this a Lewis acid. So it's an electron pair acceptor. This is a Lewis base, so it's an electron pair donor. So one other set of names that we can use for these has to do with whether they like the nucleus or whether they like electrons. Okay, so in this case, the plus, right, is short of electrons, and so it would love to get some electrons. All right, so we call this also an electrophile. Okay, so an electrophile, file is electron, You know what phile means? It means lover. So this is an electron lover. So that proton would love to get some more electrons. Okay, the base, that one already has the electrons, so it wants something more positive. And where's the positive part of an atom? Okay, the positive part is in the nucleus. So this is called the nucleophile. Right? So this means a nucleus lover. All right? So electron lovers and nucleus lovers come together to do a chemical reaction. All right, so let's write this reaction out more in the terms of an alkene. Let's see how it might react. All right, so here's our alkene. All right, I'm just going to leave these kind of empty bonds off to the side. It doesn't really matter what they're going to at this point. And we're going to react this with hydrobromic acid. Okay, so in the hydrobromic acid, we know that is a polar molecule, right? And so it has a polarity, so there's a delta plus on the hydrogen and a delta minus on the bromine, because bromine is more electronegative. Okay, so the way that this reaction takes place is that the pi bond in the carbon-carbon double bond, those are the most loosely held electrons in that alkene. And that pi bond reacts with the proton of HBr. So that H can only hold one electron, so if it reacts with the electrons from the pi bond, it has to give up an electron, and we bump those electrons over onto the bromine. Right? We know that bromine starts out with 3 pairs of non-bonding electrons, but if we follow these arrows, what we find is that H has to go onto one of those carbons. So I'm going to put the H arbitrarily on the left carbon, and the bromine gained or took that pair of electrons that were in the bond, and now it has 8. Alright, so everything was neutral to start out with. What do we got to fit over here? Alright, so bromine, if it has 8, here we can do a quick formal charge calculation. So the formal charge equals, right, the valence of a halogen is 7. And we're going to subtract from this all the non-bonding electrons, right? So there's 8, and there are no bonding electrons, and so this comes out with a formal charge of -1. So this is minus, all right? And so carbon has to balance this out, so carbon is going to have a plus. Okay, this is called a carbocation, right? And we already talked about before, back when we were talking about hybridization, that this carbocation is sp2 hybridized, and so it would be trigonoplanar. Alright? Alright, so once we react out the proton with a double bond, then we create a situation where we have 2 charged species, and that bromide with its electrons can donate those electrons to the carbocation. So we've added an H onto one position and a bromine onto the other position. Okay? So let's think about how we could describe these steps. Alright, so in the first step, what's happening in that first step? So really what we're doing is we're transferring an H from hydrobromic acid to the alkene. And so this is really just an acid-base reaction. So which of these behaves as the acid? Right? So of course that's hydrobromic acid. So this is the acid. And the alkene, or the pi bond of the alkene, is acting as a base. Alright, so it picks up the proton. So let's look at the second step here. So we have bromide reacting with the carbocation. Right? So we could call this, really, would be a Lewis acid, Lewis base reaction. Okay, so which of those 2 species would be the Lewis base? Right, a Lewis base is a electron pair donor, so this would be the Lewis base. Carbocation is a Lewis acid because it's short of electrons, so it likes to accept a pair of electrons. All right, the other way we could do these is we could call the bromide a nucleophile. Right, it has a minus, so it wants the plus, and then the carbocation here would be an electrophile. Okay, so this whole process that we've listed out here, we oftentimes call a reaction mechanism. All right, because it's showing us the stepwise process by which this reaction takes place. Right, so oftentimes these are going to, well, they're always going to involve some arrows showing the movement of electrons. But beyond this, what we'd also like to understand is how the energies are changing during this process. All right, so when we talk about reaction energies, we can typically group them into two different categories. One category involves the question of how much of the product is formed, and the other type of energy looks at how fast that it's formed. All right, so if we're looking at how much it's formed, this involves thermodynamics. Remember, and thermodynamics just describes the relative energies of X and Y, right? And so this process usually is in equilibrium, and the position of that equilibrium is controlled by those relative energies, and it's also described by something we call the equilibrium constant. Okay, so this tells us where the equilibrium is going to lie. Okay? So when we talk about how fast something is formed, that is kind of a different mode of energies, right? How fast something is formed doesn't really tell us how much of it's formed. All right, so how fast it's formed has to do with kinetics, right? And so this is a discussion of reaction rates. So how fast this process is taking place. So what is it that controls the reaction rates? We saw that equilibrium is controlled by the relative energies of the reactants and products. What controls the rate? Okay, the rate is controlled by the activation energy. Okay, and we'll look at that in just a second. All right, so we can oftentimes diagram out these energies by using a reaction coordinate diagram. All right, so in this generic reaction here, we have some molecule AB is reacting with C, and C is displacing A. All right, so this could be some kind of a substitution reaction. All right, and so our reaction coordinate diagram shows us a couple of different things here. All right, it shows us here on this side, these are the reactants. And this is the reaction progress, so we're going from reactants to products on this side. Okay, so that's the x-axis. The y-axis is typically free energy. Remember, the free energy is called, the Gibbs free energy is delta G. And so as things are low on the y-axis, they're very stable. And as they move up, they get less stable. All right, so the process usually goes from a reactant up over some hump up here, and this hump is called the transition state, right? And the energy difference between the transition state and the reactant, here, this is called the free energy of activation. All right, so the transition state is where all the bonds are being formed and broken, okay? So we go over a hump, a transition state, and we go down to the product side. All right, so let's look at how we could apply this to, or what kind of situations we can come up with this. All right, so here's two reaction coordinate diagrams, all right? And let's see what they're gonna tell us. So we're going to first discuss the thermodynamics of this. All right, and so what we'd like to know is, where does the equilibrium lie? Is it toward the products, or toward the reactants, or 1-to-1, or if we let this reaction run, where is it going to end up? All right, so the equilibrium constant is the first place that we can describe the ratios of reactants and products. Okay, so for this generic reaction, we have A and B reacting to give us C and D. The little M, N, S, and T are the stoichiometric coefficients. This tells us how many of each of those different species are reacting or getting generated. So we can say that the equilibrium constant, remember, equals the concentrations of the products, so C and D, and those are both going to be raised to the power of their stoichiometric coefficients. So C is going to be raised to the S power, and D is going to be raised to the T power. Okay, so this is the product side. Remember, and that's going to be divided by the concentrations of the reactants raised to the power of their coefficients, M times concentration of B raised to N. All right, so we can do this one or the other of two different ways. We can say that if the reaction lies more toward the product side, so if the equilibrium is toward products, what can we say about the equilibrium constant? Right? So if this reaction lies towards products, then it means that we have more C and D, more of the numerator than we do of the denominator. Okay? So that means that this number, this equilibrium number, is going to be greater than 1 because the top is bigger than the bottom. Right? So this means that the equilibrium constant would be greater than 1. If, alternatively, the equilibrium is toward the reactants, then that tells us it's toward the reactants are on the bottom, right? So that means the bottom, the denominator, is going to be bigger than the numerator, so that means that the equilibrium constant is going to be less than 1. Okay, so this equilibrium constant over here, this number, tells us in which direction the equilibrium will lie. All right, another description or another thing is the relationship between this equilibrium constant and the free energy. Okay, there's this equation that says delta G0 equals minus RT, natural log of the equilibrium constant. Okay? So in this case, if the equilibrium constant is greater than 1, so if K is greater than 1, right, that's going to mean that it's going to relate to the delta G, then the delta G 0 is going to be negative. All right, because the equilibrium constant, we take the natural log of a number greater than 1, and we get a positive number, so the whole thing will be negative. If the K is less than 1, the equilibrium is less than 1, then the delta G0 is going to be positive. Okay, so let's see where these fit in. All right, so in the first reaction coordinate diagram, notice that this distance here, down here, this is the equilibrium constant. Because the products are more stable than the reactants, that means that this is going to have a negative delta G. Negative delta G leads to an equilibrium constant greater than 1. Right? So basically, this reaction is always going to flow towards the downhill side, to the lower energy side. All right? The other one, notice that the products are higher than the reactants. Right? And so this delta G here is going to be positive. This one was negative over here. And that means, so delta G is positive, that means that the equilibrium constant is less than 1. So this reaction would rather stay over on this side. All right, so what else about free energy? Okay, so we could call this reaction, if it has a negative delta G, we call this exergonic, right? It means it's giving off energy. And if it has a positive delta G, we call it endergonic. Okay, it means it's going uphill in energy. So what is free energy made up of? Right? Is it just by itself? Well, we could say that the free energy also equals, it's also made up of two different terms. We have it equal to delta H minus T delta S. All right, so you remember what these are. Delta H is the enthalpy. All right, so that's essentially the bonding energy. T is the temperature, and delta S is the entropy. Okay, so that has to do with the randomness or the disorder in the system. Remember, for a reaction to go forward, then the entropy of the universe has to increase. All right. So, how could we calculate the enthalpy? Okay, the entropy is harder for us to get at, but the enthalpy is oftentimes a number that we can calculate based upon some tables. Okay, and in general, the way that this is done is that we take the energy, the enthalpies of the bonds broken, and this is called the dissociation energy. Oops. Let's write that better. Or in fact, the bond dissociation energy. Right? So we can sum up the bond dissociations of the bonds being broken, and we subtract from that the bond dissociation enthalpies for the bonds being formed. Remember, in general, when bonds are broken, it takes energy to do that. And when bonds are formed, it releases energy. Okay, so if in a reaction more energy is taken to break the bonds than is released when you form the bonds, then the delta H is positive, and it's not favored for enthalpy. So remember, if we have a positive enthalpy, we call it endothermic. Okay, it's kind of like endergonic, but endergonic is for the free energy. And if we have a negative delta H0, then it's called exothermic. Okay, that means that we're getting back more energy when the bonds are formed than it takes to break the bonds. Okay, so let's look at a couple of examples of what bond association energies would represent. Okay, so one example would be if we have H2, right? And we break it into two separate hydrogen atoms. Okay, so for bond dissociation energies, we're going to break the bond evenly into two even pieces. All right? Another example would be if we have ethane and we break that carbon-carbon bond in the middle, we would get two methyl radicals like this. All right, so let's look at a reaction, and I'll show you how we can use this equation to calculate the change in enthalpy, or the heat of the reaction. Okay, so let's look at this reaction here. Okay, so we're going to start with ethene, right? And so it's unsaturated, right? And we're going to react it with hydrogen. Okay, this usually requires some type of a catalyst, but we can form ethane from that. Okay, so this molecule is going from unsaturated to saturated. This is exactly the process that unsaturated fats can be hydrogenated to form saturated fats. Okay? All right, so let's take a look at how we can do this. All right, so here's a table from the book. And we're not going to be doing any of these actual calculations on exams or anything, but I want to just give you a kind of a feeling for this. All right, so the way that this would work, here, let me just rewrite this reaction over here. So we have CH2, here's ethene, and we're going to add to that H2, and this is going to go to C like this. All right, so let's think about the bonds that are being broken. All right, so we're going to break this hydrogen bond, and we're also going to break the pi bond over here. And then we're going to form this one, and we're going to form this one. All right, so in the book this is a little bit confusing because they don't totally use this, this table. So what we're going to do, so basically we're going to say that the energy change, the heat of the reaction, squeeze it in down here, is going to equal the bonds being broken. Okay, so we have the pi bond, and this is the part that's a little confusing. So in the book they say how the pi bond is, it's not on the table, is worth 62 kilocalories per mole. Alright, so we're going to add 62, and we're going to add to that the bond dissociation energy of this hydrogen-hydrogen bond. Okay, so that's right up here. Okay, all these numbers are given in kilocalories per mole and kilojoules per mole. So we're going for kilocalories per mole right now. So we're going to add 104.2. All right. So from this, we're going to subtract the amount of energy for the bonds being formed. All right. So the only two new bonds being formed, since we already had the sigma bond between the two carbons, are the two carbon-hydrogen bonds. Okay, so let's look around. So here's this one right here. So here's the carbon-hydrogen bond on an ethane. So each one of those is worth 101.1. Oops, 101.1 plus 101.1. Okay, so if we do this math, it comes up with minus 36 kilocalories per mole. All right, so what does that tell us? All right, so that tells us, because this number is negative, this reaction is exothermic. All right? Means that at least the bonding energy is going to favor this reaction to be spontaneous. All right? The actual value, or the experimental value here, is minus 32.8. So that's pretty close. Okay, this is the experimental value. Okay, the main thing we see is that it's negative, it's exothermic. Okay, so that's kind of how you would use this table, but like I said, we won't do any of these actual calculations. All right, so then the question might be posed, since we were just calculating delta H, right? How is delta H so related to delta G, right? Is something that is negative, is exothermic, is that always exergonic? What do you remember? Do you remember this from Gen Chem? So remember, this goes back to the equation I already gave you. Delta G equals delta H 0 minus T delta S 0. All right, so exergonic is going to mean that we have a minus here, right? Exothermic has a minus here. So if you have a minus delta H, does that always lead to a minus delta G? And of course the answer here is no, right? So it depends on this delta S, right? The entropy. So if this delta S is positive, then we're going to subtract the T delta S. It's going to make it even more negative. Okay, so that would say yes. So we're going to say yes if we have a positive delta S0. And we know that a positive delta S means that we're increasing entropy. It's becoming more random, and that also favors spontaneity. But we could say not necessarily not always if we have a negative delta S. In this case, the entropy is unfavorable, and so then it depends both upon the size of that negative delta S and the size, or the temperature, okay? Always, and so we can just say that it depends on size of delta S and T. All right? Because it's only the reaction is only not going to be exergonic if that T delta S term gets too big, so as the temperature goes up. All right? So this is just a little blast from the past, from Chemistry 1220. So that's basically what we want to know about thermodynamics for right now. All right, so in the next video, what we'll do is we'll look at kinetics. So we'll focus in on reaction rates and what impacts those. We'll look a little bit more about reaction coordinate diagrams, and we'll finish off by just some brief discussion, reminder about what catalysts do.